Welcome everyone. My name is Maximilien André and I'm working at l'École Centrale de Nantes. I am making this series of video in order to teach you about how to start using OpenFAST. So first, what is OpenFAST, you may ask? Well, OpenFAST is a multi-physics simulation tool designed to simulate offshore wind turbines. It is efficient and versatile. It's really fast compared to other codes because it uses a lot of assumptions. It is developed by NREL, so it's a National Renewable Energy Laboratory, and it's a really efficient tool. So why do we need such tool for wind turbines? Well, it's because modeling wind turbine and especially floating wind turbines can be really difficult because there are many different loads and physical phenomena that can affect the turbine. So first we have the wind. The wind can be of different form, and usually it's a turbulence. We have the rotation of the rotor. We have the gravity, which is pulling on the tower, the blades, and the platform. The platform is moving. We can have some vibration in the blades and in the structure. The platform itself, it's undergoing the buoyancy force. It can have forces from the waves, forces from the current. The platform is moored, and the mooring lines can have also forces from the waves and current, and they are anchored to the seabed. Turbine and the cables can be subject to marine growth. So it's really hard to model everything in one code, but this is what OpenFAST does. And to do this, it uses a modular structure, which means that each module will be in charge of some aspect of the physics involved, and the modules are coupled together by what is called a glue code. So to give you an example of the modules, we have ElastoDyn, which is the module for the structure. So this is what models the displacements of the platform and the tower and the blades, and also the vibration and the loads that they are undergoing. We have the hydrodyne module for the wave currents and the hydrodynamic loads. We have the aerodyne and the inflow wind module for the wind and the aerodynamic loads. We have the mooring with several modules that can be used. We have servodyne, which is a module for the power generation and the control system of the turbine. And the goal of this tutorial is to guide you through each of the module one by one. And we will start with the ElastoDyn module. So it's the first module and maybe the main module of OpenFAST. So today we will only use this module for our first example. So first, you have to understand that ElastoDyn will see the turbine in a particular way. Here, we have only a very limited number of different objects that represent the turbine. In fact, the turbine is only composed of the platform, the tower, the nacelle, the drivetrain, the hub, and the blades. And all these objects linked together are how ElastoDyn represents the turbine. Now, the platform is a rigid body, so it can only have 6 degrees of freedom. The tower is a flexible body, but it's represented in a particular way using the mode shapes, and we will talk about that in a few minutes. The hub is a rigid, the nacelle is a rigid body. The drivetrain can only bend in rotational direction. It can have torsional moments. The hub is a rigid body, and the blades are flexible body that can deform. So it's quite simple. All the flexible bodies are represented as beams that can bend. But in order to avoid having too much computation, OpenFAST uses the mode shape reduction. So what is this theory? Well, basically, if you wanted to represent a beam via a finite element method, you would discretize the beam in several smaller parts, and then you have to compute the interaction of each part with one another. So you have many degrees of freedom. You can have hundreds and hundreds of degrees of freedom that you need to compute at each time step. But if you look closer, you can see that the motion of the tower, for example, it's not arbitrary motion, but it's usually a combination of the first bending mode of the tower. So here we have the first bending mode, and here we have the second bending mode. And if you summarize the motion to only these two modes, we just have, we can see that the motion of the tower is roughly a sum of the two modes. So what we need to do is just know the modes of the tower beforehand, and then we need to know how much of each mode composes the final motion, and we get the motion of the tower with just 2 degrees of freedom, which are the displacements in the first two modes. So we gain a lot of computational time by using this method, and this is what ElastoDyn uses. The only drawback is that you need to pre-compute the modes before running the simulation. So now to illustrate what we said, to illustrate ElastoDyn, we will run a first example. So it will also be the opportunity to see how OpenFAST is run. So for this first example, we will have a fixed wind turbine. So you can see it here, it's fixed on the ground. There is no wind because we don't want to look at the aerodynamic forces for now. And the turbine is not rotating, so it can be pretty boring. So we added some initial displacement to make sure that something happens in the simulation. So the tower will be bent 10 centimeters in the downwind direction, and we will see how it moves. For our examples, we are not building a model from scratch, but instead we are using a reference model from NREL. So this reference is the 5 megawatts turbine that was developed at NREL and that has been widely used in the wind community since. Okay, so the first thing that we are going to do is that we are going to install the OpenFAST executable, so the software in itself. To do this, we will navigate to the OpenFAST GitHub folder. You have the address here. And we will open the OpenFAST subfolder. In this subfolder, we will navigate to the releases section with the latest versions. And then we will go to the version 3.2.1 because this tutorial was designed with this version, but you can also start using it from another version, but maybe the files won't work. The input files won't work for the version that you are using. So if you want to run the tutorial, I recommend you go to the version 3.2.1. For Mac and Linux users, you need to compile it yourself, but don't worry, it's quite easy to do. And for Windows user, we can just download the executable file. So it's this one, and then you're ready to run OpenFAST. So once your download is complete, you can put the OpenFAST executable in the home folder of the quick start. And then we will navigate to the first example and we will have a look at the input files for OpenFAST. Okay, so to run the OpenFAST simulation, I need two things. I need the executable file that I just downloaded, and I need some input files. These input files, I didn't develop them myself. I took them from NREL GitHub page, and these are input files for the 5 megawatt wind turbine. So because we are using the ElastoDyn module, we first need to set a configuration file for ElastoDyn. So let's open it. So this is what a typical OpenFAST input file look like. You have several sections. In each section, you have some key for the parameters and some value. And you also have some comments to describe what the parameter is. You have more information on the documentation that you can find online, but it's already helpful to have these comments. So in the first section of ElastoDyn, we need to set the degrees of freedom that we want for the simulation. So for example, the first degree of freedom is, do you want to allow the blade to move in the flapwise direction and in the first mode? So first will be true because we want to see some vibration in the structure. So we set it to true. And you can set all of the degrees of freedom like you want. Here, because we have a fixed wind turbine, all the platform degrees of freedom are disabled because we want the base to be static. So we don't have a surge, sway, eve, and rotational degrees of freedom. But later we will allow these degrees as well. Then we can move to the initial conditions. So here everything is at the 0 position at the beginning of the simulation, except for the tower top displacement, because as we said, we want a bit of motion in the simulation. So we set it to 0.1 meters, so 10 centimeters. Then the next section is dedicated to turbine configuration. This is what was prepared by NREL. So this is the 5 megawatt wind turbine. If you want to look at the documentation for this, you can check that all these values are the right one. But as long as we don't change the turbine, we don't need to change these parameters. The same for the mass and inertia parameters. And then we will look at the blade. So the blade can be pretty tedious to describe. So instead of having all the parameters here, we will resort to another file in which the blade is described. So we just need to specify where to look for the blade information. And because we have the same blade, we use the same file for the 3 different blades of the turbine. So let's have a look at this file. It is here. So this blade file describes the blade as a function of its length. So we have the first column, which is the blade fraction, and it goes from 0 to 1. And as we move through the blade, we can have different parameters. So we have the pitching axis, the twist, the mass density, the flapwise stiffness, and the edgewise stiffness. So all of these are used to describe the blade as a beam. So this describes only the mechanical properties of the blade and not its aerodynamic properties. And then we need to specify the modes of deformation of the blade. As we said, to use modal shape reduction, we need to have the modes. So the modes are provided in the form of polynomials here. We don't have 0 or first order term because the blade is rigidly fixed to the hub, but we have the other terms. So here the blade, the mechanical properties of the blade are described. Then we have the teeter, but we are not using it. We have the drivetrain information, but it's not really important for now. For the tower, as same as the blade, we have a file which will describe the mechanical properties of the tower. And then we move to the last part, the output part, where we specify what we want to output from ElastoDyn. ElastoDyn will compute a lot of information during its process, and by default, it will not output everything because it will be too much. So instead, we have to specify what we want to see in the output file. So here, we say we want to see the out-of-plane deflection of the first blade, the in-plane deflection of the first blade, and the tower top displacement in the fore-aft direction. If you want to look at some output data, you can access this Excel file, which is available on OpenFAST documentation, and all the available parameters are listed in this file. So for example, here I'm in the ElastoDyn sheet, and you can see that for the first blade, out of plane displacement, you have the description, and you also have the reference axis in which this displacement is given. So this file is really large, and you have all the information that you can ask from OpenFAST. So now we are done. Our ElastoDyn configuration file is complete, but we need another configuration file. Is the configuration file for the glue code, so for the main OpenFAST software. And it's this one. It's the file with the .fst extension. So we will open it and we will see what it does. So in this main FST file, you have some simulation control parameters. And here is what I want to show you. It's where you choose to turn on or off the different modules. So today we only want to use ElastoDyn. So we set 1 to the ElastoDyn value and 0 to the rest. So we are telling OpenFAST only use ElastoDyn for now. We have other things that we can specify. And here we will tell OpenFAST where to look for the for the configuration file for each module. So for ElastoDyn, we want to look into this configuration file, config elastodyn.dat, and this path is relative to the main.fst file location. So because they're in the same folder, we don't need to have a complicated path. And then you have other sim. Okay, so we are ready to launch the simulation. To do that, we will open a terminal window. In this terminal window, I will call for my OpenFAST executable. And then I will call for the FST file. And then I just have to press enter and the simulation will start. So because I'm recording at the same time, it's a bit long, but if you do it on your computer, it will be really fast. And we're done. The simulation is over. So where are the outputs of the simulation? Well, if you look in this folder, we have two new files. So one file is the out B, so out binary file, and the other one is just a plain text output file. So it's the one that we are going to open. Okay, so we have data in different columns. And you can see that we have the time, it's always the first column. And then we have the three channels that we asked OpenFAST to output. So the out of plane deflection, in plane deflection, and the tower top displacement. As you can see, the initial tower top displacement is 10 centimeters, and then the tower starts oscillating. Because I don't want to make the first video too long, we will not look too much into the data. But in the next video, we will see how to open the data with Python